Okay, Assalamu alaikum all. Today we have this third class on transmission lines, which we were discussing last time. Acha, a quick cheese, please. After every class, I post some poll on Slack, so do participate in that. Try to use Slack as much as possible, and if possible, try to post your questions in the class discussion instead of sending me a direct message so that everybody can benefit. So before I formally begin, all of you can hear me, right? If somebody can say yes or something like that, can see and all of you can see and hear me, right?
Yes, sir.
Ji sir.
Okay, great. So let's begin today. Before I start for today, very quickly, if you look over this, so last time there was a small typo. It should be a negative sign here, all right? I missed that. So please fix that we have a negative sign here in the current equation too. So, so last time in a very quickly, that we were modeling the transmission line, a two-conductor transmission line. And by modeling means that we want to know what is the voltage and current at the other end of the line. And we looked over last time that there is a finite delay because of the wave phenomena going on the line. So we took that, we catered that using these usual circuit components. And for a lossless system, we arrived at these two equations, for a voltage equation and for a current equation. And we looked over it and we said, okay, generally speaking, the solution for the voltage equation would be a sum of the forward wave and backward wave. In fact, if you see this equation, let's call that as equation 1. Let's call that as equation 1, and let's call that equation 2. If you look over these two equations, forgetting about any circuit theory or electromagnetic theory, this is just a simple second order differential equation. And from mathematical point of view, the solution for this differential equation is actually the sum of these two, or sum of these in general, sum of these two functions. Okay. Before let's write these equations again here, just for completeness. So we have this voltage equation, right? Partial z square is equal to LC partial square V over partial T square. And I'm talking about the lossless case, right? When we have R is equal to G is equal to 0. And partial square I over partial Z square is equal to LC partial square I over partial T square. So there is no difference between these two equations other than the variables. And similarly, we can write that by looking over these coupled equation, partial V over partial Z for the lossless case. We can write that partial V over partial Z is equal to minus L partial I over partial T, and partial I over partial Z is equal to minus C partial V over partial T. All right, so let's call these equation 1, 2, 3, and 4. And we last time looked over it and we said, okay, the solution for this guy in general would be F1 T minus C over V plus F2 T plus Z over V, which I said that this is a positive forward traveling voltage wave and the backward traveling voltage wave. So forward traveling and backward traveling voltage wave. So I assume this is a solution. So let's look over this mathematically, and then we'll look over more intuition of the solution. If this is the solution, if this guy is the solution, then it should satisfy this equation, right? So let's call that this as an equation 5, and let's substitute 5 in 1. Okay, substitute 5 in 1 to prove that that 5 is indeed solution of 1. Okay, so let's substitute that. So if I substitute that, what I need a left hand side with having a double derivative, and I with respect to the z, and I need this right hand side which is double derivative with respect to t. Okay, so with respect to t. So let's do that. So let's take the double derivative of this guy, partial. Okay, so let's take this guy. So partial v over partial z is equal to minus 1 over v f1 dash, right? Whatever the double derivative is. So once I take the z, it would become minus 1 over v plus 1 over v f2 dash t minus z over v. Similarly, I do to take its second derivative, and this would become 1 over v. Okay, so with the velocity, I'm going to use the symbol because so that you are not confused with this, the voltage. This is the velocity, right? Velocity. And this is voltage. Okay, so 1 over v square f1 double dash t minus z over v plus 1 over v square f2 double dash t minus z over v. So let's do the time derivative of this one so that now so that we can have the right hand side too. So partial you can see it actually very quickly. I'm going to write it directly. Partial square v over partial t square is equal to f1 double dash t minus c over v plus f2 double dash t minus c over v. So we're taking a time derivative, so there is no constant there. So what we can do now, this is the equation 6 and this is the equation 7, and I'm gonna see that this equation 6 and 7 needs to satisfy this equation 1. So left hand side is this guy and right hand side is this guy. So you can see this thing. Are they equal? So you can see this right hand side is being multiplied by LC2. So let's do that actually. Let me actually do that. So this becomes 1 over v square. So f1 double dash, I'm leaving that argument just for brevity, and f2 dash is equal to LC f1 dash plus f2 dash. So are they equal? You can clearly say that this left hand side and right hand side can be equal only if this velocity square is equal to LC. Or in other words, if the velocity is equal to 1 over LC, then you have this solution would satisfy this equation. Now you would think about it. Oh, L and C, inductor and capacitance, they are in Henry per meter and Farad per meter, and this guy is in meter per second. How come it's true? So actually, I will leave it to you. Do the unit analysis and see that once you look over the square root of this guy, and this is indeed meter per second. So this becomes the velocity. So basically, what we derived here, or what we proved here, that this guy is indeed solution of equation 1, provided the velocity on the line is 1 over LC. So that actually proves this thing is indeed the solution. Okay, so let me go back to my animation, which we were which we looked over last time. So look over this. If you look over closely, this red wave, this is a forward wave. Okay, imagine yourself. Okay, I would go show you the screenshot there. Where is the, here it is. So imagine yourself that you are sitting here. All right. So as this wave progresses, you know, in the next instant, you will be here. It means that you moved both in space and time in the forward direction. Have this picture in your mind and look over this animation. That if you are sitting on one of that peak, you will start flowing along with it. That's a forward traveling wave. And this guy has dependence or is moving both in space and time. In space, this red wave is moving in the forward direction. And this green wave, if you look over it exactly in the same way, this is also progressing in time, but it is going into the backward direction. And both are traveling waves. As you sit on one of the peak, you will flow forward. Okay, so that's the intuition. That is the intuition of this solution. And obviously this function could be anything depending upon the source, and soon we'll put up the sinusoidal sources and this would become the sinusoidal force on the exactly similar lines. And without doing that math, you can do the same thing for the current, that you substitute this solution 5, let's say, in 4, and you integrate it and you get the current. So once you do that, you know, okay, let me write that very quickly. Substitute 5 in 4 and integrate. Oops. Substitute 5 in 4 and then integrate to find I, which becomes actually I of z of t is equal to 1 over inductance times velocity f1 t minus z over v, forward traveling wave of current, minus, actually you will see a minus sign here. So the backward current has basically negative sign, say that it has a phase shift of 180 degrees, or it's an opposite sign. So this is I plus minus I plus. So don't forget that there is a negative sign with the current, and I'm gonna, this negative sign comes from mathematical point of view, and I'm gonna tell you from intuition to why this negative signs make sense. Just bear with me for 2-3 more minutes. So this LV, if I do the unit analysis of this inductor times voltage, you can see this inductor is voltage second, or amps meter, times meter per second. So this is actually, if you see, volts or amperes, which is ohms. So this LV is kind of ohms. You can see this thing from your circuits or from basic physics, that I is equal to kind of V over R kind of thing. So we here in transmission lines, we call it this as Z naught, special symbol reserved for it. LV is equal to, and we call it as a characteristic impedance. Okay, so that's a characteristic impedance, LV. And you can also have another form of voltage we just figured out, velocity we just figured out, square root 1 over reciprocal 1 over LC, which is same as L over C ohm. So this is an equation for the characteristic impedance. So we can say this thing, that the current is actually equal to 1 over characteristic impedance F1 T minus Z over V, minus f2t plus z over v, which is I plus I minus. Now, if you look this equation, you have this equation in your notes. This equation, let's call that, this is 5 equation 5, which was the voltage solution, and let's call this is an equation 7. By inspection, you can clearly see by comparing the two, you can see that the positive, or the forward traveling current is same as forward voltage over Z naught, or this is same as that forward voltage is current times that. But these are the usual relationships. A little bit difference here for the negative, for the backward way, for the backward current, there is a negative sign with it, or V minus is equal to minus Z naught I minus. Now the question is, why we have a backward current as a negative? So the intuition for this, now hear it very carefully, the intuition of these two solutions. So this is my two conductor line, which we started modeling. So what happens that this line is being energized by a positive voltage, right? And this voltage is being accompanied by positive current, right? So this is accompanied by the positive current, and both of them are being linked with the characteristic impedance. So in other words, you can see this thing that as the wave is traveling, this voltage and current wave, they are seeing the Z naught, the characteristic impedance of the line, the inherent, or you can intuitively think that inherent resistance offered by the line at each point is this characteristic impedance, okay? So, and obviously, we are always interested in energy transfer or information transfer. So these two waves, they are carrying the information or energy or power in this direction, you know, in the positive direction, okay? So when we look over the other side, when the wave is going in this direction, so here, you know, this again, you know, positive, negative. So this one is the negative wave associated with the voltage, okay? And this is again positive and negative terminal of the line. And this is being associated with a, okay, you have to speak up. I cannot read the chat. If there are any questions, please speak up. I Z of t negative. So that's going into the opposite direction of what this current is. And they are basically carrying the information or power towards this side, towards the negative side. So you cannot have both voltage and current as negative, otherwise the information of or the information would flow in the same direction. You will see later on in the course, actually we are solving vectorial equations. These you know, electromagnetic fields would be flowing here, and we'll see that later on. So this sign convention becomes important there. So current is only negative for the power transfer, okay? So any questions here? So I'm going to move on with the further concepts. Okay, so we actually, what we did so far, we looked over a general model of a transmission line, and I can't emphasize more than this, that basically we have started looking over the math of this intuitive animation, which you're seeing, that there is a forward traveling wave, this red one, and when it hits when it hits a change in a medium, then there is some transmission and there is some reflection, and both forward and backward wave are present at the same time on the line. And eventually, although I'm seeing these two lines as differently, but eventually you would see that this one, okay, let me show you the other one. So basically this, at any point, this is the resultant of these forward and backward wave. And because of this superposition of the forward and backward wave, you will have very interesting effects would be happening on the line, which we're going to explore now. So far we looked over the general lines. Let's target discussion of the sinusoidal sources only. Sinusoidal, so sinusoidal propagation, basically, you can say that. And why we are interested in that? So basically, sinusoidal propagation means that these functions f1 and f2, which I was writing it as generally general functions, will change them to the sinusoids. So why sinusoid? You know, from your basic preliminary courses earlier, that anything can be any signal or any function can be represented by a combination of many sinusoids, basically your classical Fourier series or Fourier transform. So if you know the response of a system for a one sinusoid, you can predict the response to any combination of sinusoids and hence any function. That's why we are studying sinusoids. So let's look over the sinusoids, some basic fundamental stuff which you may have already seen before we start our formal treatment of sinusoidal propagation on transmission lines. So few things first, actually, and make sure pay special attention to that. There's a very fundamental stuff which often students get confused over it. So I wrote this one, f1 t minus z over v and f2 t plus z over v. So in terms of sinusoids, what we can do that there is some, let's say, some amplitude of a sine, and you call it omega t minus, that's a t, and remember this is a wave, it needs to have both the dependence of t and z. So omega t minus beta z. So I have introduced a symbol here which I'm going to shortly explain what does it mean. So this guy would be omega t plus beta z. So few things first. So if I'm writing it for the voltage, the unit of this guy is volts. This guy is also volts. So let me remind you a few things here. Let's look over some basic fundamental stuff. You know a cosine function V naught cos omega t. So you know this thing. What is this guy? That on a time axis, this is doing this thing, right? On a time axis, where omega is actually related with this time period. Time period is related as 1 over f, and omega is 2 by f. So you used to call this omega as, you know, angular frequency, or, you know, radian, yeah, angular frequency, or you could have said just frequency, right? In the units of radians per second. So I'm gonna start calling this guy as temporal frequency, right? Should not be any problem. Just naming you temporal means that I'm referring to a temporal frequency. And you know that fundamental thing is that the argument of the cosine or sinusoidal function has to be in radians, right? So this is radian per second, this is second, so this becomes radians. So that's the mathematical fundamental stuff. The argument cannot be other than radians. So now if I say this thing, you know, without any problem, if I say this thing, that I have write another function, cos beta z, okay? You know that mathematically I have to be correct. This is in the unit of radians. I can't have anything other than units of radians. We know that this is the unit of meters, z. So this beta is in the units of radians per meters. So this is again a frequency. This is again a frequency, no problem in that. If you call omega as a frequency, you will call beta as a frequency. But I'm gonna say this as a spatial frequency. Nothing changed. Fundamentally, nothing changes. The variables change. This is again a cosine on the axis of z. on the axis of z, and here this would be on the axis of z, in the same way as this was on the axis of t. But here this beta is the spatial frequency. ठीक हो गया? So now if we combine the two, which is our wave cos omega t minus beta z. This is a wave because this function is changing in time with the temporal frequency omega, and this is also changing in units of distance with the spatial frequency beta. Okay, and this one is radians per second, and this one is radians per meter. You do not, this is nothing new. You put all your earlier elementary concepts which you learned for omega, you can apply those for beta too, because mathematically there is not much difference. अच्छा, अब question ये है कि one thing which I want to remind you again, that this when we're talking about a wave, you know, and remember, don't forget this, we defined the distance between the two peaks, or you know, this guy, this is also lambda, as one wavelength. And we said that the basic definition, don't forget that. I know many of you in earlier class have seen, they forget the distance traveled by a wave in one time period is the wave length. Okay, isko bhulna nahi hai. This is the fundamental stuff. And then you see this thing, this time period, you recall this is the frequency. So basically, and obviously, agar main isko radians mein le jaun, if I put another axis here in angle or theta, this guy is 2 pi. You know that from your basics. So I can easily write a relationship. I can easily write a relationship which connects all of these things. So for z is equal to lambda, means one wavelength, this argument beta z, if I'm looking just over it, just for time being, you know, for time t is equal to 0, I'm looking at cos beta z. Then for z is equal to lambda, beta z is equal to lambda is equal to 2 pi. Okay? Because in one time period it's wavelength, and one time period is also equal to 2 pi. So beta lambda is 2 pi, and beta, the spatial frequency, is 2 pi by lambda. See, huge similarities between the two. This angle, this temporal frequency was 2 pi f. In fact, I can easily do this thing, 2 pi, our fundamental relationship, velocity is equal to f lambda. So lambda is equal to velocity over f. So 2 pi f over velocity. So beta and omega are related with like this. So all are related, nothing different. This is spatial frequency, this is temporal frequency, and they are being related with the velocity. So that's something very fundamental. I would like to ask you few very fundamental questions here. If I ask you, tell me, if I write this function v naught cos beta z, is this a wave? If I write another function like, you know, v naught cos omega t, is this a wave? Is this a wave?
No, sir.
Okay, great. These both are not waves, right? These are just mathematical function. For the wave, it's very important that you need to have both the time and distance dependence. Otherwise, wave का तो काम ही है कि information को आगे ले जाना, और वो information तो तभी आगे जाएगी जब time और position दोनों change होगी. So again, I'm going to take you here because it's a very fundamental and important point. I know students get confused on this. So if you go back to this, imagine yourself sitting on one of those peak. You can move forward only if you are changing, if this wave is moving both in time and space. Here in the animation, you can see this is moving in the space or up. If you put up a stopwatch with it, and time is also changing, and that's how the information propagates. If any one of the component becomes frozen, it's not a wave, and information will not move forward. Okay, so to make things more interesting, let me ask you this thing. What kind of this function? This guy is this guy, omega t plus beta z, or cos omega t minus beta z. These are pure traveling waves. Pure traveling waves. That the wave is fully traveling. Okay, how about, and I'm not going to answer that, I want you to think later on, how about cos beta z cos omega t? Is this a wave? Okay, I will answer that only. Yes, this is a wave because both z and t are there. But what kind of wave is this? I won't answer that, and I want you to think for it later on. And how about this guy? Cos omega t minus beta z plus cos beta z cos omega t. Is this a wave? I want you to think about it. And I want you to think about what kind of wave is this? Okay. So these you need to have these things in your mind throughout the course. The concept of the forward wave, the concept of the backward wave, and what do you mean by wave? And this beta, this is a very important parameter to understand this course. Beta, again, let me say a few more words on beta. So beta is radians per meter. So let me give you another interpretation of it. So omega t minus beta z is a forward traveling wave, and let's say for time at an instant of time, obviously time is changing. I'm seeing at an instant of time this cos beta z. So this is in the units of radians per meter. If I multiply, let's say as an example, I take beta as 2 radians per meter, a number मैंने shoot किया. So at z is equal to 1, my beta z is what? 2 radians. At z is equal to 3 meters, my beta z is 6 radians. What does it mean? It means that the wave accumulated a phase of 2 radians after traveling a distance of 1 meters, or the wave accumulated a phase of 6 radians after traveling a distance of 3 meters. And again, इसका क्या मतलब हुआ? इसका मतलब ये भी हुआ, you can also think, remember, you can also think in this way, when you reach here, let's say at z is equal to 1, you already, if you start from here, you already accumulated 2 radians. You can also think that this was the delay. You can convert this in time, that this was the amount of time you took to reach from here to here, or this was the delayed you experienced while reaching here. So phase, delay, they all mean same thing. And when we talk about phase, we are specifically talking here for the sinusoids. So very fundamental concepts, and make sure that
can you please,
yes.
So
yes.
Can you please repeat this last concept?
So
regarding beta.
Okay. So if you put up some numbers here, all right, if you put up some numbers here, let's say beta is 2 radians per meters and z is 1 meters. So when you multiply these two, beta z, it means that at z is equal to 1 meters, because ये क्या होगा? Cos ये बीटा जी है वो तो खैर वोल्टेज आ जाएगा वहां पर, जितना भी वोल्टेज आएगा कॉस बीटा जी जब मैं एवेल्यूएट करूंगा। लेकिन इंपॉर्टेंट बात ये है कि if this guy accumulated a phase of 2 radians after traveling a distance of 1 meters, या अगर मैं इसको completely लिख लेता हूं cos omega t minus beta z, this guy has accumulated in space 2 radians at a distance of 1 meters, अगर बीटा बताओ, ठीक है। सो इट्स जस्ट अ मैथमेटिकल कॉन्सेप्ट, लेकिन उसकी इंट्यूशन जो है फेज कांस्टेंट, जस्ट अ फेज कांस्टेंट। जैसे जैसे आप अगर आपको बीटा जी में प्रॉब्लम हो रही है समझने में, while you're reviewing it, you think in cos omega t, you understand that well, and whatever you learn in cos omega t, apply on beta z, just change the dimensions, and here you go, you would have the same thing। ठीक हो गया? Okay, so before we formally begin, which I think we would begin in the next class, I want to review few concepts further. You can see this thing, or you can see this thing that जब हम ये बात करेंगे, let me go back about the solution of the voltage, right? कहाँ गया ये? जब मैं sinusoid की बात करूँगा, so this would be what? Cos omega t minus beta z plus cos omega t plus beta z, right? We know. Now, when you imagine this thing, when I look over the solution for these equations like these, if I try to solve these equations in time domain, things would be very complicated. Things would become messy. Things would become untractable in many cases. So in order to ease our analysis, we look over complex numbers. We look over exponential notations to ease our analysis. We look over the phasor form, just like many of EEs have already seen in the circuit theory, some phasors. I'm going to review that so that who are the students who forgot it, they can quickly catch up what I mean here. So let's take a detour and let's look over some complex numbers again for few next 15 minutes or so, right? So that we are all on one page, because we would be using them for representing our sinusoids for this. So I can say this thing that complex numbers or functions. So here I mean complex numbers by means a plus jb. Complex functions are very easy to handle in differential equations, because हमने वो जो model बनाया है वो एक temporal differential equation, it's a massy differential equation. We want to make it easier. So in differential equations, these becomes very easy in complex numbers. So complex number क्या है? Complex number is something you can say x plus j y, which is on a complex plane. You can think like this is a point, this is the real plane, and this is an imaginary plane. This is z point, whose argument, whose distance from the origin is x plus, this point is this. And basically, in this guy is rotating with the speed omega t, जब हम उसकी बात करते हैं sinusoids की. So if you recall this thing, Euler identity, और फिर मैं इनको connect करता हूँ. Euler identity क्या है? E plus minus jx cos x plus minus j sin x. ठीक है? So basically, a complex number, when it is rotating with a frequency omega, then we have the real part and the imaginary part of the sinusoids. Let me actually show you this quick animation here for you guys. So if you recall, I know all of you know this, just I'm reminding you. So you see this on a unit circle. as it is rotating, the complex, this z is equal, इसका जो real part है, वो this blue one is your cosine function, and imaginary part on this is a sinusoid. You know that, okay? And that's basically related with the Euler identity. So going back to do this, we can also say this thing that cos x is equal to e plus jx plus e minus jx over 2, and sine x is equal to e plus jx minus e minus jx over 2j. ठीक हो गया? And where j is your imaginary number, j is square root of -1, or j square is equal to -1. It's very easy to prove this Euler identity actually. अगर आप वो e j x को series में खोल लो, so one portion would be cosine and other portion would be sine x. You can open that as a series. So I won't go into those details. So in other words, you can see this thing. ये बताने का मकसद ये Euler identity. You can see this thing that cos x and sine x can be transformed into exponential functions, exponential complex functions, by this Euler identity without any problem, because you can see this thing. This is equal to what? E plus jx over 2 plus its complex conjugate. Okay? And this is e minus jx over 2 plus complex conjugate. It's one and same thing. So if I go back to my voltage, let me write my voltage here. VZT is equal to V naught cos omega t minus beta z. Okay, right. Let me write it like this: plus minus beta z. I can write that like this. Real of V naught V naught e j omega t plus minus beta z, right? इस पे किसी को इतराज नहीं होना चाहिए. Look over this Euler identity. Euler identity is ejx is equal to cos x plus j sin x. So I can say, मैं real लिख देता हूं साथ, and I write it in exponential form, and I can easily convert this cosine function into the exponential form. ठीक हो गया? फिर उसके बाद I can easily, I can drop this thing. I can drop this real part, and I will later on bring it back. Again, for mathematical convenience, I drop that. So V naught e j omega t dot e j. Okay, इसको मैं थोड़ा सा आसान करता हूँ. इसको मैं प्लस रखता हूँ अभी, बाद में मैं चेंज करता हूँ. So e plus j beta z. ठीक हो गया? So I actually represented, if you see this thing, e plus j beta z and e j omega t, this v of z of t. I represented this Euler sinusoidal function in the exponential form, like this, by using the Euler identity, and this makes the analysis very, very straightforward. And we can define here that, let's say हम इसको अगर drop कर दें, E's know this thing, but for the physics students, this might be a little bit new, but this is not hard to grasp. You can say that if I drop this ej omega t, I am going to define a voltage which is just the function of e j beta z, and this is known as the Phasor voltage. Why I drop e j omega t? Because the source, once you put the source on a transmission line, its all likelihood, the frequency, because a linear system, the frequency would not change. The frequency is fixed. I'm talking about temporal frequency. This would stay the same. So we can say, okay, let's drop this e j omega t and let's just deal the spatial frequency. Time dependence is there, temporal frequency is there, but let's drop that from the mathematical analysis. And this is known as the phasor analysis. And basically, this is true for only sinusoids. Don't mess this up. Only sinusoids. And this is true for,
Sir?
yes.
Sir, if temporal frequency remains the same, then why does spatial frequency vary?
Because velocity can change. Because beta is omega over velocity, and velocity can change. Velocity can change. Anything could happen.
And what causes the velocity to change in transmission lines?
The change of the medium, some complicated load, and anything. Temporal frequency can only be changed in a nonlinear system. In a linear system, temporal frequency can never change. But spatial frequency, it is a spatial thing. You know, it depends upon the space thing. So it can change due to, you know, whatever the reasons. ठीक है, so that's true. So अच्छा, अब एक चीज बड़ी इंपॉर्टेंट है यहाँ पर, जो स्टूडेंट्स मैस अप कर देते हैं. अगर मैं आपसे कहूं cos ओमेगा t प्लस, लेट्स से लिखा हुआ है pi by 4, let's say ये 2 है, तो I can say this thing 2 pi by 4, right, without any problem. ये आप लोगों ने देखा हुआ, लेकिन I can also say this thing 2 ej pi by 4, right? So this is 2 ej pi by 4, this in exponential form, and with the j that represents a phase. ठीक है, that represents a phase. As an example, अगर मैं इसको देखूं, अगर मैं यहां से वापस जाऊं, you know, वापस जाऊं, ऊपर जाऊं, जितनी भी j की टर्म्स है ना, they will translate into these arguments, right? अगर मैं वापस backwards करूं, एक मैंने सिस्टम सॉल्व कर ली एक्सपोनेंशियल फॉर्म्स में, डिफरेंशियल इक्वेशन सॉल्व कर ली, एक फाइनल रिजल्ट आ गया है, एक्सपोनेंट से मैंने वापस रियल सिस्टम में जाना है, तो दिस, अगर मेरा यहां पर लेट्स से, यू नो, एज एन एग्जांपल, यहां पर एक ये मेरा लगा हो टर्म e minus 3, that's it, e minus e minus 3z, ये लगाओ मेरा. अब मैं जब ये बैकवर्ड जाऊंगा तो ये e minus 3z किधर जाएगा? कोई बता सकता है मुझे? Can anybody tell me where this e minus 3z would go when I go backward? इसके साथ j नहीं मैंने लगाया.
It's a constant.
So basically what would happen, मैं यहीं पर दिखाता हूं, what would happen जब मैंने इसको वापस उसमें कन्वर्ट करना है. So what I'm gonna do, let me do this thing. एक काम करते हैं, यहाँ पर मैं करता हूँ, because this is a fundamental thing and students confuse. Let's say एक फंक्शन है 3e minus j 4z, you know, and e minus 2z. इसको मैंने वापस, ये मेरा फेजर वोल्टेज है, इसको मैंने वापस टाइम डोमेन में कन्वर्ट करना है. So what I'm gonna do, I will multiply first, I would bring back ej omega t, right, जो मैंने ड्रॉप किया था, and what I'm gonna do, I'm gonna put all the j's together, plus j omega t minus 4z e minus 2z, and then I will bring my real part back, 3 ej omega t minus 4z e minus 2z, okay, and once so no, real इधर भी जाएगा, right? अब real में जब करूंगा, so e minus 2z तो already real है, right? So 2 minus e, it's already real, so ये बाहर चला जाएगा. So ये जो है, this will transfer back to cos omega t minus 4z, and this would lead as it is. So यहाँ पर एक टेक होम मैसेज जो आप लोगों ने थ्रू आउट द कोर्स नहीं भूलना, जब भी j लगा होगा किसी भी जगह के ऊपर, क्योंकि हम एक्सपोनेंशियल फॉर्म में करेंगे, कॉम्प्लेक्स फॉर्म में करेंगे, दैट रिप्रेजेंट्स फेज। जहां पर j नहीं लगा होगा, दैट इज द पार्ट ऑफ द एम्पलीट्यूड इक्वेशन, दैट वाज द पार्ट ऑफ द एम्पलीट्यूड। ठीक है, डोंट मेस दिस अप, फंडामेंटल थिंग है, इसको कभी गड़बड़ नहीं करना। दिस इज फंडामेंटल कॉन्सेप्ट। वेयरएवर यू हैव j, that's that representing phase, and wherever you have, you know, some real thing, that with basically you can see this thing, e minus 2z kahan chala gaya, idhar, this is this guy. So this becomes, अब अगर मैं इसको प्लॉट करूंगा, so ये along the, yes
सर एक मिनट थोड़ा ऊपर कीजिएगा।
जी जी,
यहाँ आपने इक्वेशन में आपने खुद से एक वैल्यू इंट्रोड्यूस करा दी है,
ये e minus 2z।
जी सर, इससे थोड़ा ऊपर जी सर, यहाँ पे सिर्फ अब यहाँ से जो आप अगली लाइन पर आए हैं v is equals to 3, जो पहली लाइन है v की,
ये वाली,
जो आप सेकंड लाइन पे आए हैं जी सर,
हाँ,
ये e j ओमेगा t आपने खुद से इंट्रोड्यूस,
क्योंकि फेजर की डेफिनेशन में हमने e j ओमेगा t को ड्रॉप किया था। ये टेम्पोरल फ्रीक्वेंसी है, ये एग्जिस्ट करती है, ये खत्म कहीं नहीं हुई, ये तो हमने मैथमेटिकल कन्वीनियंस के लिए ड्रॉप किया। इट्स देयर, द सिस्टम इज एट ओमेगा, ओमेगा इज देयर, व्हाटएवर द फ्रीक्वेंसी इज, लेट्स कॉल दैट, यू नो, लेट्स से 10 kilohertz है, 1 gigahertz है, whatever it is 1 gigahertz forever, it cannot change. So we dropped it, we के okay, हम 1 gigahertz पे एनालिसिस कर रहे हैं, we don't care इसको लिखे ना लिखे, बाद में लिख लेंगे। And that's the essence of the phasors.
लेकिन सर मैथमेटिकली रॉन्ग नहीं हो जाएगा वो उसको स्टेट करना इस तरह?
नहीं, क्योंकि रॉन्ग इसलिए नहीं होगा क्योंकि वो यहाँ पर था, मैंने खुद ही मैथमेटिकल कन्वीनियंस के लिए इसको ऑलरेडी ड्रॉप किया था, वो तो था शुरू से ही वहां पर मौजूद था। e j omega t is there, it is there, it's not being dropped. ठीक है, so I think that's what I have for you today. Next time इसको प्लीज ये अपने फेजर कॉन्सेप्ट्स को इसको बड़े क्लियरफुली देख के आना सारी चीजों को ऑन वेडनेसडे क्लास, बिकॉज इसको फिर हम उन डिफरेंशियल इक्वेशंस के ऊपर प्रॉपरली एनालिसिस अपना स्टार्ट करेंगे। सो दीज फंडामेंटल कॉन्सेप्ट नीड्स टू बी इन योर माइंड। ओके, सो मैं यहाँ पर स्टॉप कर देता हूँ रिकॉर्डिंग। अगर किसी का कोई क्वेश्चन है तो